So good morning, everyone, and welcome to this session on socio-technical smells. Today, we are going to explore 5 different socio-technical smells as well as their resolutions. And the kind of underlying theme here is that seemingly hard organizational problems can be improved via refactoring and code improvements. And I like us to start by exploring why software is hard. So please have a look at this piece of code. It's 19 lines of code. Who can tell me what this code does? Who can tell me if this code is correct? I have to admit that, I've been coding for more than 3 decades now, and I find it really hard to understand what this code does. And still, it's only 19 lines of code. A modern system looks very much like this, where we have hundreds of thousands, maybe even million lines of code that looks like that. So I like to claim that a modern system can outscale the human brain and our cognitive capabilities. Adding to that challenge, our modern system is also a moving target because we have tens, maybe even hundreds of developers working on that system, right? So it kind of changes all the time. And this is the challenge we're going to try to pick up today. How can we gain insights into what actually happens in these systems? And the first socio-technical smell we're going to discover is something I call the overcrowded system. And this is something I unfortunately have first-hand experience with. So let me tell you a story about a death march. And by the way, this is the book I always wished that I could write. Now, what happened here was that it was a couple of years ago. I did some work for a large product company. And this company, they had a project that had been going on for 2 years. It was a critical project. And unfortunately, they had missed deadline after deadline. And now the situation was critical. So I was called into a management meeting. And they asked me, is there any chance you could take a look at this project and see if you can rescue it? Because we have our next deadline in 3 months, and if we miss that one, the company will be subjected to some pretty heavy fines, right? So it would be really expensive. And I said, yeah, sure, I can take a look at it. And they said, yeah, and feel free to do whatever you have to do. So I said, okay, cool. So me and a colleague start to investigate the ongoing project, start to investigate the code base. And after a while, we went back to management, and we said that, we actually have some good news. We think we can deliver this in the next 3 months. And they were really relieved, as you can imagine, right? So they said, yeah, that's great news. And we said, yeah, indeed. However, you're not going to like what we're going to do. Because what we're going to do is that we're going to take all that code that's been developed for 2 years, and we're going to throw it out. So this was code developed by 25 people over 2 years, and we're going to throw it out, and we're going to start from scratch. After they recovered from that shock, we tried to explain that, it's not like we're starting completely from scratch, right? Because that existing system can serve as our prototype. After all, it was pretty successful in exploring the edge cases and where the hard parts are, right? So we're going to learn from that and feed that learning into the new version we're building. So they somehow balked that, right, to some extent. And to this day, I'm still surprised that they gave us the go-ahead, but they did. And then they asked, okay, so how many additional people are going to need, right? And I said 5. So they said, okay, so you want to go from 25 to 30 people? Yeah, that's doable. I said, no, you're misunderstanding me. We want to be 5 people in total. And the reason we could say that with confidence was because both me and my colleague have read the Mythical Man-Month. And the Mythical Man-Month is best known for what we today call Brooks' Law, that adding people to a late software project makes it even later. And this is one of my all-time favorite books. It's an absolutely great read, and I highly recommend it. And what I like about it is that Brooks, the author, he also includes a formula that I have plotted to you here that explains why this happens. So what you see here is that on the x-axis, you have a number of people on the project, right? Number of people you can add to a project. And on the y-axis, you have the number of months until completion. And what you see here is that to a certain degree, we can add a few people, right? And we get a quicker completion date, a faster completion date. That's good. However, there's also some kind of turning point. And beyond that point, we can see from this curve that each additional individual that we add becomes a net loss, leading to a longer completion time. And this might be a little bit surprising, but what it's all about is that, each individual increases the coordination and communication costs. And at some point, that increase in coordination and communication is, simply going to outweigh all those extra hours we get available and then some. So that's why we fall into this trap. When that happens, there are really just two things we can do. The first and perhaps the simplest choice, the one we choose for this project I told you about, was to kind of rescope, right? To kind of shrink the organization to fit the size of the software system. So that's what we did when we went from 25 people to just 5. The other option is really to go back to a drawing board, redesign and re-architect so that our system can accommodate more people. And this is much, much harder. And this is something that we're going to look into throughout the rest of this session. Before I go there, maybe you're curious how it went with that project. Did we really ship in 3 months? How many of you think we managed to pull that off? Seems to be a majority. Yeah, good, of course. Otherwise, I wouldn't be telling you about it, right? But in fact, we didn't ship in 3 months. We only needed 2.5. And what's so fascinating about this, and the reason I tell you this story, is because it kind of indicates the amount of waste we create when we fail to pay attention to our socio-technical fit. And I've been thinking about this ever since. I mean, the Mythical Man Month, the book, it was published in 1975, and it tells, lessons from a project developed in the 1960s. So why do we keep repeating these same mistakes? I mean, the story I told you about, it might be an extreme case, but I see it almost on a weekly basis in various companies that we to some degree fall for Brooks' law. So why are we doing that? I think I have an explanation that I'd like to test on you. So please, have a look at the following piece of code. Who can tell me if this code is a major coordination bottleneck for our 5 different feature teams? Or if this code is all developed by one person? No one, of course. You cannot tell. And the reason you cannot tell is something I like to call the grand tragedy of software design, that we, the people that build the system, were invisible in the code itself. A piece of code simply doesn't reveal anything at all about its socio-technical context, yet it's such a vital piece of information. So how can we get that information? That's the very purpose of a set of analysis techniques known as behavioral code analysis. So how many of you are familiar with behavioral code analysis? So it's like, okay, maybe 20% of you. Good, good. So a behavioral code analysis is a little bit different because in a behavioral code analysis, the code itself, the way it looks, if it's easy to read, low on complexity, all that stuff, it is important. It really, really is. But it's even more important to understand how we as an organization interact with the code and system we're building. So that's the main piece of information in behavioral code analysis. And we're going to see several examples on behavioral code analysis during this session. And I'm going to show you what type of data I use for that. And the first example I want to give you is about another socio-technical smell. It's about coordination bottlenecks in code. So let's have a look at that. I started out by showing you a small piece of code. Let's now look at an architecture. So this is like my generic software architecture. This is what like 90% of all business applications looks like, right? So we have a bunch of boxes representing subsystems or maybe even services. And then we have a couple of different data sources. And of course, we have various clients, right? So we might have mobile clients, Android, iOS, and so on, web clients. We might communicate with other systems via REST, and so on. And already here, I would like to claim that it's virtually impossible for a human brain to grasp all the details. And we really don't do that. What we do instead of grasping all the details is that we use something called mental models. So as a programmer, we very rarely remember a particular piece of code line by line, right? Instead, we have an abstraction in our head on simplification that allows us to reason about something as complicated as code. We have a mental model representing that code. Now, mental models, they are a prerequisite to reason about something as complex as a large system. But mental models are also sensible, because the more developers work in a piece of code, the harder it becomes to maintain a stable mental model. And this is something I would like to show to you. So let's pretend that you write a piece of code yourself today. 5 days later, you look at that code again, and now you see that 7 other developers have been working on that code in the meantime, right? So your original mental model is now outdated, and you need to spend time kind of rebuilding it, which is wasteful and can be painful. And if this is something that kind of continues week after week, then you're basically going to be in a constant onboarding mode. Or you're going to go to a code and you're going to make changes to it based on an outdated mental model. And that's one of the reasons why there is this strong correlation between access coordination as seen in the code and software defects. So if we have an important barrier standing between us and a healthy, sustainable code base, like coordination needs in code, we should watch out for them. So how can we do that? Well, there's a behavioral code analyst that just does that. And to do a behavioral code analysis, we obviously need some behavioral data. And this is data that we can fetch from our Git logs. So here's a simple example. So if we're after coordination needs in code and excess number of authors work in a piece of code, what we do here is simply we scan our Git repository. And for each file that we find, we look at, okay, how many people have been contributing to this file over a given time period? Typically like 3 months. On some projects, we might go even further back and look at the whole year. And these type of Git analytics, they are like, they're really crying out for automation. So you can use some simple command line tools. So this is a tool suite that I open sourced a decade ago. It's called CodeMat. And you can just point it to a Git log and it will calculate a table for you like this. So looking at that table, I see that on this particular system, the number one potential coordination bottleneck seems to be in the build system, because I see this builder file, right, has been modified by 13 authors in a period of just 3 months. So it looks like a very crowded place. So getting statistics like that is a good starting point. But it also makes it a little bit hard to spot patterns from a tabular representation. So what I tend to do is to visualize things. So let's look at a visualization of coordination needs. And now I have picked up another code base. This is Folly, a modern C++ library from Facebook, right? And there's really nothing special about Folly in this case. I just want something that's a little bit larger. And in general, I'm a big fan of visualizing things, because by visualizing things, we tap into one of the most powerful pattern detectors there is in the known universe, the human brain. So let's see what we can learn from visualizing coordination bottlenecks. The way you read this visualization, if you have seen my previous talks, you're probably familiar with the style. It's something called enclosure diagrams. And the way you read it is that each one of these large circles that I'm pointing to here, they represent a top-level folder in your Git repository. And inside those folders, right, if this was your code base, the names of those folders would typically be important subsystems or high-level modules or maybe even services. And then at the lowest level of detail, we see that each file with source code is visualized as a circle too, a colored circle. And the size of the circle just reflects how many lines of code you have in the file that you visualize. The important aspect here is the color, because the color reflects the author density. Right? So the more people work on a piece of code, the more red it becomes. Perfect. Now that we know how to read that visualization, we're ready to see what we can learn. So looking at Folly here, I like to think that the package to the left really pops out. So this is something about async socket programming, right? It seems to have a very high author density. So let's zoom in on it. When we do that, we see that these files have been modified by 58 people, and this is over the past year. So 58 people over 1 year. That basically means that each week, there's a new developer coming into that code. How should you possibly maintain a stable mental model of that code, right? So when I find something like that worries me, I always try to dig into it and try to understand the root cause. And when it comes to coordination in code, more often than not, the root cause is technical. So let's pick up this piece of code. So this is a small snippet from Folly. And I do respect that a lot of people here reading C++ on a Tuesday morning might not really be your thing, right? But don't worry, you don't really need to know much about C++ because there are always a couple of patterns that we can look for. So what I typically do is that I skip out the details and look at the patterns. And one pattern that always worries me is this one, where you have a special case, right? A conditional statement. And below it, there's a long explanation in a code comment. 9 times out of 10, this is a clear sign that what you have here is a separate responsibility, right? That we should have extracted into a function or maybe even a class and put a good name on it so that we can reason about it, right? So there seems to be too many responsibilities here. The second thing that worries me, high level, are these complexity patterns, right? Because you see there are like these blocks of nested complexity sprinkled around the function. This is code that's cognitively challenging, right? It's hard for the human brain to reason about nested complexity. So when we combine these code smells with the fact that what you see here is really just a fragment of the total class, right? The total class has like hundreds of functions that look like that. Then I think it's a fair assessment to say that we have identified a God class, right? So how many of you are familiar with the God class smell, right? So like maybe half the audience, good. So a God class is basically a design smell that we use to describe classes which compulsively collect responsibilities and have a complex implementation, right? And the problem with the God class is not only that they're hard to understand, it's also that they kind of tend to centralize the behavior of the system in the way that each time I want to make a change somewhere in the system, I end up having to modify the God class, right? And over time, they just grow more and more complicated. And this is a problem from an architecture perspective, right? God classes really are the traffic jams of the software world. So what does it mean to a developer organization? Well, it simply means that God classes, they kind of act like magnets, right? So they kind of force programmers potentially working on different team, potentially working on different features into the same class, right? So this is where you experience these unexpected feature interactions, complex merge conflicts, stuff like that. So what can we do about God classes? Once we have identified them, we need to act. And the kind of fundamental property for being able to scale the people side of code is cohesion. So a God class is low on cohesion. It has way too many responsibilities. And we see that this is really just one example. There are lots of research papers on this that kind of show that, when we get this access coordination that the God class encourages, then we end up with systems that are both wasteful and fragile. So what can we do to improve the situation? Let me show you an example. So far, I have been torturing our C++ code base, right? So I think it's only fair that we pick up Java, right? Let's do that. So this is our Java code base, Hibernate. It's an object relational mapper, one of these lovely things, right, that were quite popular like a decade ago. And I've identified a God class in Hibernate here. It's a God class called Abstract Entity Persister. But let me assure you, there's absolutely nothing abstract about this class, right? It's a massive class. In fact, it contains 380 methods, right? There's a lot of really, really complex logic in there. So I like to think that if you just look at that list of method names, we see that, the method names are kind of like all over the place, right? So there seems to be multiple responsibilities going on here. So what do we do in this situation? Well, the first step is, of course, to identify the various responsibilities of that class, right? So I tend to start by just moving methods around and trying to group them inside a class according to responsibility. And once I've done that, what I tend to do is I tend to extract them, try to put a good name on them that kind of describes that behavior. So I go from having a large gut class into having smaller class sets, each one a little bit more cohesive. And of course, this increased modularity makes it easier to reason about the code, makes it easier to maintain it. Because let's say I'm working on the lifecycle aspect. Right now, there's a natural place for me to look for any behavior related to lifecycle, right? So it helps with the readability. But there's much more to it. Because from a social perspective, what we do with the highly cohesive design is that we create natural boundaries for developers working on unrelated aspects, right? So I can increase the amount of parallelization, the amount of work in parallel I can do. So cohesion really is a fundamental property for minimizing coordination in code. Now, that was coordination inside the same class, but a potentially even more interesting aspect is intermodule coordination, right? So let's talk about dependencies and the cost of change. And I like to start with this statement that, to me, not all dependencies are equal. What do I mean by that? Well, what I mean about that is that most of the time when we talk about dependencies, what we talk about is the stuff we can see in our code, right? So I have a piece of code here, uses some code over here. They kind of depend upon each other. And I like to claim that if we kind of restrict ourselves to this static view of dependencies that we see in the code, then we will miss out on two important aspects. The first thing we're going to miss out on is that the most interesting dependencies tend to be invisible in the code, because those dependencies tend to be logical rather than physical. To give you an example, let's say you have two services here, right? They are tightly coupled, but of course you cannot see that in the code because they kind of communicate via an asynchronous message bus, right? That's the kind of information we want to have. Second, if we just look at the code, our data isn't going to be particularly actionable. And the reason I say that is because most dependency analyzers, they kind of come out like this, right? And the reason is because any non-trivial system simply have so many dependencies. And some of these dependencies are expected. They are exactly what we want, right? So we would somehow need a way to separate the good from the bad dependencies so we can focus our attention where it's likely to be needed the most. So let's revisit dependencies through the lens of cohesion. And let's in particular talk about package cohesion. And when it comes to package cohesion, I want to show you two contrasting examples here. So in the first sketch here, I see that I have two packages, and I see that the dependencies between them seems to be well managed, right? So that is like one clear entry point to each one of the packages, right? And those are the only dependencies we allow here. I also see that inside a package, I see that the various elements, they kind of seem to be connected. So that's a good thing. That kind of indicates that, yeah, everything in that package kind of belongs together. So this is like the design I would like to see. Contrast that with the design with low cohesion, right? Here we see that we have this web of unmanaged dependencies, right? That kind of go all over the place, but basically everything in one package is connected to everything in another package. And not only is this going to be really painful to work on, it's also going to be really, really painful to do any amount of work in parallel there, right? Because change is going to ripple over modular boundaries. So how can we identify and visualize those type of dependencies? Well, let's first take a step back and consider a very fundamental fact of code. Code changes for a reason, right? We don't just modify code at random. I mean, if you do, we might have bigger problems than cohesion, right? So what that means is that software architecture is all about making those changes easy, be they bug fixes, new features, or non-functional requirements. And the big question, of course, is how well does our software architecture hold up? Are we working with or against our software architecture? So what if we could evaluate our actual modification patterns, the way our code evolves, against the desired patterns as indicated by our software architecture? This is the purpose of another behavioral code analysis technique called change coupling. So change coupling is about finding patterns in files or services or even functions that kind of co-evolve over time as defined by various commits. So I'm going to show you a simpler view of this. Let's boil it down to a simple system with just 4 different files, right? So this is the entire implementation. And I see here that when I make a change to a system, the first time I'm modifying the login module, the chess module, and the dial-up module, right? That's it. The second time I make a commit, I'm changing something else. But the third commit, I'm back to modifying the login module and the chess module together again, right? So now I start to see a trend, and if this is a trend that continues, I know that there has to be some kind of logical dependencies between login and chess, right? Because these two modules co-evolve all the time. They are coupled by change. And change coupling is something that let us reason about the cost of change. And we can also use it to visualize package cohesion. And I want to show you an example. And of course, after going through our C++ and our Java code base, the time has come to C# and .NET. So this is a code base from Microsoft. This is ASP.NET MVC Core, right? This framework for building dynamic web applications. And it's the same visualization style as you saw before when we talked about coordination. The only difference is the colors carry a different meaning. The colors show how healthy that code is, right? How hard it will be to understand. So everything that's green, that's good. Everything that's yellow means that this code is high on complexity. But that's not the aspect I want to focus on here. What I want to focus on is the coupling. So let's zoom in on this package that I'm hovering over called integration tests. And let's reveal the change coupling between those tests. So we see that there seems to be some heavy change coupling as indicated by those lines. What does that mean? Well, it means that when I make a modification to one of these integration tests, I have a predictable change to 6, 7 other tests. Does that make sense to you? No, it looks a little bit strange, right? I would be a little bit worried about this because the consequence for me as an application programmer would be that I make some tweaks to application code and now I have like 7 failing test suites that I need to attend to. That's painful, right? So I would use this information to dig into the implementation and see, okay, is there any aspect that we failed to encapsulate, right? Maybe we copy-pasted some test conditions or something like that, right, that leads to this explosion in change. So change coupling can very often help me ask the right questions from the code. But looking at it from a package cohesion perspective, I see that, all right, yeah, but it might be problematic, but at least the coupling is limited to code inside a specific package, right? So it's a local problem. And local problems are always better, right? Let me show you another example. So this is an end-to-end test for that code base. And I see that when we make modifications to that end-to-end test, we have a predicted modification to code in 3 other packages. This looks ridiculously expensive and fragile, right? This is how we can easily introduce flaky tests, right? Because it's hard to remember to update all these tests. So this looks expensive. And these are really just 2 examples, but they kind of indicate an important principle of change coupling. That change coupling in itself is neither good nor bad. It really just describes the way it is. So as such, we always need to contextualize our change coupling findings. And I want to show you the 3 typical patterns that you're likely to come across when you investigate your own code base. So let's look at the first example here. So what do I have here? Well, I have 2 modules that are change coupled, but I see that one of them is a unit test and the other one is the code endo test, right? This is good coupling, right? This is the type of coupling we want because it kind of indicates that our tests are being kept up to date. Now, let's look at a little bit more complex scenario. Let's look at this one. So what do you think about the coupling here? Well, this is a model view controller system, right? An MVC system. And we see that each time I change something in the view, maybe I add a new button or whatever, then I have predictable changes in the models and the controllers, right? Is this good or bad? Well, it's good in the sense that it actually matches what I would expect from the MVC pattern, right? It pretty much follows architectural principles, and that's always a good thing. And of course, I can always ask myself the question, is this really meaningful to kind of have these cascading changes? Could there be a simpler pattern I could use, right? But for our purpose right now, I would say that this coupling matches our expectations, and that's good. Now, I saved the best for the last. This is one of my favorite code bases. This is Telegram for Android. And I want to show you an example of what change coupling looks like with a God class. So the module I'm highlighting there in the middle, the large red blob, that's something called a chat activity, which sounds like a pretty central class to Telegram. And we see that it's heavily coupled, right? And that's what kind of God classes do, right? No matter what part of the system you work on, you end up in the God class, right? So it has tight dependencies to like 20 different files in various pieces of the system. So when evaluating change coupling, what I always recommend is that you evaluate it according to architectural patterns, right? So you make sure that the coupling, the actual modification patterns, follows what you expect. And change coupling in general is problematic once you start to violate those patterns. And the reason I say that is because when you start to violate your architectural principles, you're basically introducing a surprise. And surprise really is one of the most expensive things you can ever put into a software architecture. So please avoid. Now that we're talking about dependencies, dependencies of course have a social context too, and dependencies are going to constrain how the people organization can work. So in particular, what happens when we add the team dimension to a tightly coupled system, like the one we saw from Telegram, for example? What would it look like to put multiple teams on that code base? Well, basically what would happen in a tightly coupled system with multiple teams is that you would be playing shotgun surgery, right? A shotgun surgery is basically when you want to make a tweak to some part of the code, and now you end up having to visiting 15 different files, potentially owned and developed by multiple teams, right? So we're going to kind of destroy the mental models for each other all the time. So it's a really, really expensive problem. And the way to solve it is, again, cohesion, right? So it's if we kind of manage to rethink the architecture, remodularize it, so that we can kind of express the problem domain in code, then we're also going to create these natural team boundaries, because that tends to be the level at which we can parallelize work. So we saw an example earlier with Hibernate. So I would address the change coupling problem in very much the same way. Now that we have discussed dependencies in a team context, I'd like us to look at a related topic, knowledge distribution. And this is really, really important. We're now going to look at some individual analysis. And the reason I think that's important is because getting the people side of code wrong has killed more projects than even Visual Basic, right? So let's drill into this. I'd like to share a story with you. This is something that happened to me not that long ago, 3-4 years maybe. So what I tend to do in my day job is that I help companies identify and manage technical debt. So I did this workshop in Germany for a team. And they had 2 code bases that we kind of analyzed, right? And of course, we identified some technical debt. There were some things that we agreed we should do differently. But overall, these 2 code bases looked pretty good. But then, towards the end of the day, someone kind of revealed that, we have a 3rd code base as well. So I said, super interesting, let's look at that one, we still have time. And everyone kind of just started to give each other funny looks, right? And then someone said that, no, we really don't have to look at that one, because I think the technical term he used was a mess, right? That code base was a mess. So I said, okay, yeah, now we definitely need to look at it. So we picked it up. And when I do this analysis, we have all types of objective numbers, right? We can measure code health and all that stuff. So we did. And it turned out that this 3rd code base, objectively, there was no quality difference compared to the other 2 code bases. And this was, of course, super surprising, right? So what we had to spend some time picking up code examples, looking at the code. And after a while, everyone kind of agreed that, there really is no objective difference in quality between these 3 code bases. So why was the third code base considered a mess? The reason for that third code base being considered a mess had nothing at all to do with the code. The third code base simply had a different story. The third code base had been developed by a different team in a different part of the organization, and that team had since been disbanded, and the new team had simply inherited that code. So the reason that they thought it was complicated had nothing to do with the code. It was all about unfamiliarity with the solution and the domain. And it's very easy to confuse a lack of familiarity with complexity. And when we do that, we're going to solve the wrong problem. Because what this team needed wasn't a major redesign of that code, right, or a rewrite. That would have been a waste of time, right? What they needed saw proper onboarding and time for learning. And time for learning is also something that's related to the socio-technical space. So how many of you were here last year when I talked about the business impact of code quality? A couple of you, and you still returned. Wonderful. That's nice. So what I talked about last year was the research we've been doing called Code Red Papers. And what we did was basically that we took each piece of code, categorized it as being either green, healthy code that's easy to understand, low in complexity, and then yellow and red code, which is unhealthy. You know, you have maintenance challenges, growing technical debt, complex implementations, all that bad stuff. And what we did with that research was that we proved that if you have green and healthy code, you know, you can complete tasks significantly faster. In fact, you can complete tasks 10 times as quick compared to the most complex code. So there is a huge business advantage to having healthy code. However, when we did this study, we also had a lot of granular data. And when we start to look at the data, we kind of saw that there is quite some variability, particularly when it comes to these really complex pieces of code, right? They seem to be extremely unpredictable. And what we wanted to investigate was if the person aspect could be one part of the explanation. So does it matter which programmer that makes a change or, you know, fixes a bug in a particular piece of code? I guess we've all seen that context, right? Where you have this, you work in a company, most of the code is pretty okay, but there's this system over here that no one really understands except person X, right? Who's been maintaining that for 10 years. Now, unfortunately, person X is on vacation and you need to step in and fix something, right? That's not a fun place to be. So this is what we decided to investigate, and we published a paper on it earlier this year. You're going to get the reference at the end as well. And what we did here was that we simply looked at, okay, how much more expensive is it, you know, to come as a new developer? And when I say new developer, I don't mean that we're like fresh out of school. I mean, we simply haven't worked in that part of the code before, right? How much more expensive is that versus a person who has worked more extensively on the code? And what we figured out goes pretty deep, because what we found was that for small changes, like maybe these one-line bug fixes, you will need 45% longer to make that change compared to someone that already worked with the code. And when it comes to more complex changes, like you know, maybe implementing a new feature, you're going to need twice as long as someone that already worked on that code. But notice that these numbers, they're only true for unhealthy code, yellow and red. For green and healthy code, there is no significant difference, meaning that in green code, onboarding costs are likely to be very, very cheap compared to complex code. Did I manage to explain that? Some of you nod. I really like that. Thank you. And these findings, they're really, really far-reaching when we consider another common force that acts upon software projects, the truck factor, right? So how many of you are familiar with the truck factor? So like a third of you, maybe. Good. So the truck factor is also known as the bus factor, or my personal favorite, the lottery factor. But they all refer to the same thing. How many developers can leave before your code base becomes unmaintainable? And the truck factor is particularly worrisome when it kind of collides with unhealthy code. So if you have unhealthy code with a low truck factor, that's something I like to call the highway to legacy code. And I want to show you an example of this. So now the time has come to pick up a JavaScript code base. You've been looking forward to that, haven't you? Right? How many of you are React developers? Wow, that's a lot of people, 20% maybe. Have you ever looked under the hood at the React implementation? So we're going to do that now a little bit. We're going to touch the surface at least. So React, according to GitHub, has 1,500 contributors. That's a lot of contributors. So what would a truck factor be? And the truck factor here is simply measured as how many people can leave before we lose detailed knowledge of 50% of the code. With 1,500 people, I would say maybe it's, I don't know, 150 people, 100, 70. Turns out when you measure it, the truck factor is really only 2 people. So out of 1,500 people, if 2 people, the wrong 2 people leave, all the code that's indicated in red is where you will lose detailed knowledge. Now, this is indeed a very, very common pattern. It's nothing unique to React at all. And to kind of prove that, I want us to look at the main competing framework in the JavaScript world. So this is the truck factor in Vue.js, where if 1 person leaves, you know, the creator, you lose like 80% of the code. Still, I have to admit, I would be a little bit more worried about React, even if Vue has a lower truck factor, because there's another piece of information here. If you see here, some of these circles, they have a dashed border. That's something I use to indicate unhealthy code. And we see that there are more instances of unhealthy code in React compared to Vue. So Vue kind of seems to be in a better shape implementation-wise, which we just learned will ease our onboarding, right? But still, even in Vue, there seems to be this unhealthy place with a low truck factor. It's something called a compiler. I'm not a Vue programmer, so I really don't know, but maybe a compiler is important. And the reason I say this is because code quality issues really do amplify organizational problems. So my recommendation to you is to let community smells, like a low truck factor, be the driver for refactoring, right? So prioritize improvements on unhealthy code with a low truck factor. And that is the most important refactoring. It's not necessarily about fixing the worst code, right? It could as well be about mitigate socio-technical risks, like the truck factor. So with that covered, we have come towards the end of our socio-technical tour. And what I wanted to show you today is that when we do software design, we also do social design. More specifically, I wanted to show you that I find it so fascinating that seemingly hard organizational problems can be reduced via technical improvements, right? We can solve things via technical improvements that no amount of reorganization or team patterns can solve. And today, I want to show you how by designing for a socio-technical alignment, not only can we get a simpler onboarding by flattening the learning curve, we can also reduce, significant risks like key person dependencies, right? And we've also seen how our cohesive design helps us to couple teams, right? So that we can kind of, increase the amount of work we can do safely in parallel. And we have also seen how a highly cohesive design that allows minimizes coordination in code can minimize defects. And finally, one of the nice benefits of all of this that's really, really important is that doing these things is also going to improve team morale. And those are really, really strong statements, so you will be relieved to learn that all of them are supported by research. And I've added links for you here. You're going to get their presentation sent out to you after the talk. If you want to dig deeper into this, all visualizations have been done via CodeScene, right? So CodeScene is the thing I've been working on for the past 8 years. If you want to test it out in your own code base, you're very welcome to do so. It's free to test it out, even on proprietary. So if you like this, please consider to support us. Finally, since it's Tuesday morning, I think it's perfectly fine with a little bit of self-promotion. So if you want to dig into all of these socio-technical aspects, then you could probably do worse than checking out my new 2nd edition of Your Code is Crime Scene, where I have a couple of chapters that go into all these different smells with various examples. So with that covered, I'm really looking forward to questions, and I'd like to take this opportunity to say thanks a lot for staying here with me. Thanks a lot to conference organizers, and may the code be with you. Thank you.